Okay, so next up is linear programming, and this is a standard um, um, what would I call it, methodology for optimizing systems. If one can represent that system as a system of linear equations, and it's pretty useful in that way. It's used for lots of things. So in my area of transportation, this is a big deal with optimizing pavement management systems. So optimizing investments and making improvements with limited resources. It also has a real application in the traditional. You have X factories and Y number of trucks and so many drivers and so much capacity at each location and the costs associated with them. What's the optimal operation for that system? That's a linear programming problem. So anyway, typically there's an objective function that's either maximized or minimized as a function. So the output is a function of inputs. We want to typically optimize that in some way. So this may be a cost, for example, or something else. Maybe it's a production function. We want to maximize that. But then we have a set of constraints on what values those x's can take. So for example, the factory example that I used, you have so much capacity at each factory. You may have, the trucks that you use have, maximum load, right? Those kinds of things. So there are constraints on the values that X can take on. And it's always a linear assumption. So what this does is it assures a solution space is convex. And there's an optimal solution somewhere, and it's at a corner where two lines intersect. So here's an example of a minimization problem, and I want to minimize this value subject to these constraints. Now I can do this graphically because I only have two values or two variables here, x1 and x2. So the way that's done is to plot the constraints. It's a nice way to start because then you see what's actually happening. You can plot the constraints, find the feasible region, that is where on the graph are all of the constraints satisfied, and then plot that objective function on the graph and see where it first hits the feasible region. So I have an x and y plot, or an x1, x2 plot, and I'm going to plot the constraints. So the first constraint, if I set x2 equal to 0, then x1 is 1,000. I didn't bring the constraints up on this slide. There's not enough room, but you can go back and look at them. Take my word for it. If you set x1 equal to 0, x2 is 600, and plot that line. So this is the line that represents constraint number 1. Constraint number 2, oops, I don't know what happened there. If I set x2 as 0, x1 is 1500, and similarly for x1, 0. And I can plot that constraint. And then the third constraint is here. So x2, 0, x1 is 700, and so forth. There's the plot of that line. There's a fourth constraint that I'm not showing here explicitly, but it is that x1 and x2 are both positive. So everything has to take place in this first quadrant. Okay, and where are all of the constraints met on this graph? Well, they're all on this side of the lines. The easiest way to check it is to check the constraints at x1, x2 equals 0. You find that they're all met. So this point is in the feasible region. So every line is a less than, right? So I could actually fill in or color in the region of space that is less than that constraint, and where they intersect is right here. This is the region in which all of the three constraints are met, and it's greater than 0 as well. Okay. So now what I want to see is where does the optimization function or the objective function show up? So I can actually plot that for different values of z, and I can just kind of move it down, keep moving it down until it hits one of the corners of the constraints region, the feasible region. And this is the first point it hits, so this is the one. This is the solution. So the idea here is to define the control variables, establish the objective function, and establish constraints. You'll be doing that with a set of real data from problem 5.7, I believe, in the text, the ASA text. I've given you the solution to that, by the way, but I would ask that you try it first and see how you do, and then you can bring up the solution and see where you went wrong. Okay. And then I'm going to ask you to convert that problem to the standard setup. Okay, and use this simplex method to solve the problem, that homework problem. So the first thing to do is the standard setup is a maximization objective function. Always maximize using the simplex method. Always express it as a maximize problem, and then set all the constraints so that they are less than or equal to. There are no greater than or equal to's allowed, so you have to fix that. Okay. So once you've converted it, you can then move forward. So here's that same example. Is it I think it's the same one. I'm using an x and a y instead of x1, x2. So this is minimized, but I have to change this to maximize to get it into a standard setup. So I can just multiply this by -1, and this is the same thing. If I minimize this, I've maximized this, and vice versa. So that's the first step. And then I want to make sure that all constraints are less than or equal to. If they're not, then you have to multiply them by -1, and that changes them. That reverses the sign. And then I'm going to convert all equations, the constraints, all the constraints to equalities using slack variables. And then okay, I'm going to go through this. So this is the first constraint, second constraint, third constraint. So these are the slack variables expressed as equals. And I'm going to move all variables to the left and all the constant terms to the right. So this is my setup now. I want to minimize or maximize this subject to these constraints, but now I've got all equal signs and I've got all the variables on the left and all the constants on the right. Now I'm ready to start using the simplex method to find out, really all I'm looking to do, what are the x and y values that will maximize my objective function. So I'm going to create a table where all of the coefficients of all of the variables are in it, and the rows represent the equations. There are 4 of them, right? And then the columns represent the variables. So if I go back here, I have 4 equations and 1, 2, 3, 4, 5 variables. And then of course I have the constant terms. So 6 columns and 4 rows will do it. So let's check that out. By the way, that's called a tableau. So here's my equations, and here's the tableau. You can see the coefficient of p is 1 in the objective function, which is the first row. So I've basically just taken these numbers from this set of equations and plugged in the coefficients into this table.